Welcome back. For this example, we're going to find the volume of a solid, which is bounded by the plane z equals 0 and the surface z equals 1 minus x squared minus y squared. All right, let's think about this. What is this surface? Remembering back, we should recognize that this is a paraboloid opening down with a y-intercept of 1. So let's think about this graph in 3 space. So we've got x, y, z. I will put a 1 up here. If we're trying to graph this, it's going to be a paraboloid opening down. It's circular with a radius of 1. And so it's going to be intersecting z equals 0. Z equals 0 is the xy plane here at the origin. So we have a circular base of radius 1. Try and make that look good. And then it is coming down like this. So we have this circular base here, right? And when we see a circle, that might be something to indicate to us that we need to use polar coordinates. Let's think about trying to set this up with rectangular coordinates because everything's given to us in terms of x and y. So what would that look like? Let me give myself a little more space here. There's my y. All right, so finding that volume enclosed or bounded by this circular or elliptical paraboloid and the xy plane. Well, trying to set this up, we need bounds in terms of x equals and y equals. So I'm going to have a y equals function here. I'm going to use constants for x there. My x values are going between -1 and +1. What are my y values bounded by? My y values are bounded then by the circle. How can we define that in a variable way? So if we think about that circle on the base, that would be like saying 0 equals 1 minus x squared minus y squared. Or I could move that y squared over. Y squared equals 1 minus x squared. Isolating that y, I've got y equals plus or minus the square root of 1 minus x squared. So my y is now defined by this circular region. So I could say, well, y equals negative square root of 1 minus x squared, and y equals positive square root of 1 minus x squared. And of course, then we would put our function, and our function is that elliptical paraboloid, so 1 minus x squared minus y squared. And then we would have dy dx. I'm running out of space, but that's dy dx. Those are my, that's my order of integration. So does this look ideal? The point of me setting it up this way, and I have talked about this probably longer than you needed me to, is that this doesn't look ideal. It's an option, but we don't want to deal with it. We could do it, right? I could integrate with respect to y, I could integrate with respect to x. I would just have a lot of algebra, especially when I plug these guys in. So what would be a better way to set this up? And again, we see a circle. I see x squared plus y squared. Well, I could factor out a -1. So I've got -1 x squared plus y squared. So let's think about that. If I set that up in polar coordinates, my theta would go from 0 all the way around the circle to 2 pi. And what would my radius be? My radius starts at the center. 0, and extends out in all directions to that circle of radius 1. So r equals 0 to r equals 1. If I think about redefining this, I could factor a -1 out, so I'd have negative the quantity x squared plus y squared. So here I could say 1 minus r squared. Don't forget your extra factor r, and then we write dr d theta. And so hopefully most of us look at this second integral set up in polar coordinates and say, that really makes more sense to use polar coordinates. It's going to simplify my calculations in the long run. So let's do it this way. We've got v 0 to 2 pi. I'm going to integrate, I'll do it like this, got my integral from r equals 0 to 1 of r minus r cubed, distributing that, dr d theta. So working on the inside and using the power rule to integrate with respect to r, I have r squared over 2 minus r to the 4th over 4, evaluated from 1 to 0. Plugging in 0 doesn't matter. I'm going to get 1/2 minus 1/4, which is positive 1/4. So I have the integral from 0 to 2 pi of 1/4 d theta. I can put the 1/4 in front if I'd like. Integrating with respect to theta, that's going to give me 1/4 theta. We need to evaluate from 2 pi to 0, which gives me 2 pi over 4 minus 0 over 4, or pi over 2. So in this example, we found the volume, and we noticed that we were dealing with a lot of circular regions. We had x squared plus y squared. We converted it to polar, and it was super simple to evaluate. All right, so I hope that helps. Good luck out there. Email me with any questions.